So in this part, we'll talk about coding theorems. We'll see how the first two parts come together. So I'd like to remind you, this is the problem of sending classical information using quantum channels. Okay, so we have a classical message, M, that consists of k bits. The encoder maps these bits to a joint state of the input systems A1 through N. Each one of them goes through this noisy quantum channel N from A to B. And then the output, we have a noisy version. Now, Bob would like to estimate the original message. So he performs a measurement. The measurement outcome is M hat. Then we look at the performance of a given code, a given pair of encoding and decoding mappings. So the coding rate is the fraction of information bits per transmission, K over N. You would like to have a high coding rate. And the error probability is the probability that the estimation is wrong. We want this error probability to be small for every message that Alice can send, no matter what the message is. Okay. Then we also defined in the first part of this tutorial an achievable rate. We say that the rate R is achievable if there exists a sequence of codes such that the error probability tends to 0 as the code length grows to infinity. This is a very strict requirement. Yes?
Yes, like the term that we're using, what is the difference between a sequence of code and just like the code?
Yeah, so here we look at different code lengths. Okay, the code length is N. So for a given mapping, a given code, given encoding and decoding mappings, you're talking about also a fixed N, right? But here I'm letting N grow from 1, 2, 3, and so on. So for every length, every value of N, there is a different code. And this is what I mean when I say a sequence of codes. We do not get 0 error probability for a finite, for a particular value of the code length. We get 0 asymptotically. And now we define the classical capacity of a quantum channel. It's called classical capacity because we are sending classical information through a quantum channel. This is defined as the maximal achievable rate. So it characterizes the best performance that we could ever hope for in classical communication, in transmission of classical information. So let's start with a classical channel, the model that Shannon considered, where the channel is modeled by this conditional probability function, P of y given x. This is the probability that Bob receives a classical output y, given that Alice sent a classical input x. So Shannon showed that this is the formula for the capacity. We can compute this simple expression for the capacity. We don't need to go through all the different mappings and optimize over and take the limit of n growing to infinity in order to calculate the capacity. We can compute the capacity by this simple formula. It's called a single letter formula because it doesn't depend on the code length and it doesn't contain any limits inside. Here what we have is the mutual information between x and y. I'd like to remind you that we think of this as the correlation between those two variables. So if this area is the randomness in x and then the right part is the randomness in y, the mutual information is the overlap between them. That's the intuition. So we have a fixed channel. We have this conditional probability distribution. And we look at some input distribution, P of x. When we multiply P of x times P of y given x, what do we get? The joint distribution of x and y, right? So then we need to calculate the mutual information with respect to this joint distribution. And we maximize over all the possible input distributions. This is, you want the highest rate possible.
I want to look at the worst case.
No, but you can choose how to encode. This has to do with the encoder.
So suppose the maximum is achieved when P of x is concentrated on a single message, then it's not interesting.
No, but in this case, it's 0, right? So it's definitely not the maximum. Right? If it was the minimum, then it would be 0. Now, I remind you, those are some identities that we've seen last time. And we've looked at this bit flip channel that flips the bits with a probability of 1/4, if you recall. So now I would like to compute the capacity of this channel. So I want to compute this maximum, but I can also write the mutual information using this identity. It's the entropy of y minus the conditional entropy of y given x. But if the channel flips the bits with probability of 1/4, the conditional entropy is equal to H2, the binary entropy function, for the value of 1/4. And then I am left with maximum of this entropy. The maximum, this entropy is also entropy of a bit. Okay, it's binary, so it is equal to 1. What do we get? We get 1 minus H2 of a quarter. If you remember from the first, I know it's been some time, but in the first part, we've seen codings or a proof idea, a proof concept of a coding scheme that achieves this rate. Now we see that this is the capacity, meaning what we achieved in the first part is actually optimal. It is the best that you can ever do. This is the highest communication rate of classical information that you could ever achieve reliably.
Can you remind me why hy of x is h2 of epsilon? What was it? Is it a basic thing?
Okay, so we can represent the channel this way, right? When with an XOR operation with this Bernoulli quarter variable, right? So instead of writing h of y given x, I can write that it's h of x XOR z given x. Correct? You agree?
Yes.
Yeah. Now, when I condition on x, okay, if x is equal to 0, for example, I have just z. If x is equal to 1, I have z not. But it doesn't depend on x anymore. I mean, okay, in any case, this is equal to h of z. This is equal to h2 of a quarter. Okay? Because you condition on x, you don't need to worry about it anymore. So you are left with the entropy of the noise, which is h2 of a quarter. Okay? Now let's move on to the quantum case. Here we have a quantum channel n from A to B. Now the formula is a bit more complicated, but let's try to understand what is going on. So here we have the mutual information between a classical variable W and the quantum output of the system B. Of course, you would like to know what is W, right? So in this formula, we maximize over an ensemble of states for the channel input A. So we look at a set of input state phi A, where W is an index of this collection of states. We also have a distribution over this collection of states. Then I can also look at the average of rho WA, the density matrix that describes the joint state of the classical system W and the quantum channel input A. Then I apply the channel and I get the joint state of W and B. Then I compute the mutual information with respect to this state, and now I maximize over all the possible ensembles of the channel input. Okay? So basically, I maximize over all the possibilities of W. This is, just before I answer the question, I know it is confusing because W did not appear in the channel model. There was no W in the coding problem. W is only a part of the formula that will be an achievable rate, but it's part of the formula, but we maximize over all the possibilities for W, and therefore this formula does not actually depend on W after the maximization. Yes? In the special, it is, okay, in the special case of a classical channel, they are equal. But I think I won't have enough time to show this, okay. Should I show you? Is it important for you? No, I think it's, yeah. I leave it as an exercise, okay, yeah.
Over what do you think the maximum? Over the distribution W or over the ensemble?
Both. Over all the ensemble, over all the possible collection of states, and over the distribution over those collections. But of course, to compute this, you also need a bound on the size of this collection. So there is a bound, as you can see in the bottom part. We do have a bound. It's, I haven't defined this notation. This is actually the dimension, the square dimension of the input state. This is the bound on the size of the collection that I need to optimize over. So this is actually considered to be a computable formula. You can compute it numerically if I give you some channel. Yeah, and yeah, maybe I haven't said, I should say, this is called the Holevo information of the channel. Okay, it's denoted by chi of n. Okay, so now I give the HSW theorem named after Holevo, Schumacher, and Westmoreland. The first part of the theorem, let's consider a given channel. Now the rate R that is equal to the Holevo information of this channel is achievable. It is possible to communicate at this rate with an error probability that tends to 0. This implies that the classical capacity is bounded from below by the Holevo information. It doesn't mean that it's equal to the Holevo information. It only means that it's bounded from below. Why is that a straightforward consequence? Because the classical capacity is defined as the maximum of the achievable rate. So the maximum is higher than any particular achievable rate, okay? Now, when you look at the general channel, it's a bit more complicated than just packing spheres as we've seen last time, but we still use this picture. We still imagine that there are small spheres that we pack inside a large space. The proof is based on an argument that is called Shannon's random coding argument, a classical argument that Shannon used. He said, let's just choose the code words at random. Let's start with a random codebook that is distributed according to an IID distribution with this PW, or in the classical case, it will be P of X, okay? And then, in the quantum case, we also prepare states that depend on this code word. Then the decoder performs a measurement that projects onto those, we think of them as small spheres. They are called typical spaces. Okay. And it turns out that the overall dimension of the output is approximately 2 to the power of n times the entropy of B. And the small sphere has dimension that is related to the conditional entropy. So now, similar to what we've seen before, the number of spheres, 2 to the power of k, I remind you that for every message we have a different sphere. The message consists of k bits, therefore the number of messages is 2 to the power of k. And now it is bounded by the overall dimension divided by the sphere dimension, which turns out to be 2 to the power of n times the mutual information. Therefore, the coding rate has to be lower than this mutual information. This is the rough idea. I know I'm not really showing you how the proof works, but because it's a bit involved.
So maybe you could say some words about how I pick code words in the phase space. I mean, it's clear how to choose in the computation space what will be the kit that would be after as the code words. But right now I'm not sure that I understand what could be a right superposition code words. Okay, so let's suppose that I decide that 0 and 1 would be code words. So now the plus state.
Yeah.
How we should treat that.
But it really depends on the channel. So maybe I'll give a pretty trivial, just a second. Sorry, so, okay, I'll give a simple example. N of rho is equal to 2 half rho plus half sigma x rho sigma x. Okay, so this is the quantum version of a channel that flips bits with probability half. Right? You see this half? If I have a qubit state, there's probability half that I will get the exact same state, and there's probability half that I will flip the bits. If I look at the classical channel, let's denote it by P of y given x, the capacity of the corresponding, the analogous channel, do you have an idea, a guess? 0, yes. Why? Yes, if y is equal to x plus z, and z is Bernoulli half, then y and x are statistically independent. There's no correlation between the input and the output if you flip the bits with a probability of 1/4. Therefore, you cannot transmit any information over this channel. What about the quantum case? The classical probability of this quantum channel is equal to 1. Why? Because I can transmit, I can transmit plus and minus, and the channel doesn't affect them at all. Right? If I want to send the message 0, Alice will send plus.
So I missed the point that you are looking for classical capacity and not quantum capacity of the quantum channel. So yeah, I guess.
Okay.
So sorry.
No, it's okay. I think it was a good opportunity. I saw people nodding, so I think they were happy with the example. Okay. Thank you for the question. Good. Okay. So we've seen a lower bound on the capacity, but what if I want to compute the capacity? So I want an equality. According to the last part of the HSW theorem, I can compute the Holevo information of the product channel n to the power of tensor k. So first I take 2 copies of the channels, and then I take 3 copies of the channels, and so on. And I need always to compute the Holevo information, normalize by 1/k, and then take the limit of k going to infinity. So here I have an explicit, not explicit, I have a formula for the capacity. This is not a computable formula. I cannot compute this. This is too difficult to compute. So this is not considered to be a full solution to the problem.
Because of the K limit?
Yeah, because of the limit, because it involves limits. Yeah, it's difficult to compute this. Why is it difficult to compute? Because the dimension of the product channel, the dimension of the Hilbert spaces, they are exponential in K, right? So it's too difficult to compute. There was another question. Yes.
So the capacity you said before, that's achievable. It's not achievable with product state encoding?
Yes. That's actually very related to what we'll see in the next. I think it's the next slide. But
Where does this relation come from? It's just complicated.
To show that you have a formula of this form with a limit is actually considered to not that difficult to show. Why? Because the capacity is defined as a limit, right? You take the limit of the block length to infinity as the maximum of all the.
Chi was just a lower bound of the capacity.
But what?
The chi was
it
just
was
a
low
lower
bound.
bound.
Yeah.
Why, if I take many copies, I get the correct capacity?
Well,
Magic.
we'll see. No, it's not magic, but it's not a short proof. No, I try to think if I can show it with.
No, it's not a short proof. Okay.
Yeah. It's kind of based on continuity and the data processing inequality. So, okay, maybe later because it's too much, I think. Okay. No, this is not an average. This is, you normalize because you encode over, okay. Yeah, it's like I encode k blocks of size n, okay? If I encode with, maybe let's use big K because it's not too confused with the number of bits. It's like I use k blocks, each one is of size n. For each sub-block, I use the encoding that achieved from the previous theorem. And then I check what is the rate. But now this is the overall block length, right? This is, let's call this n tilde. So when I check what is the rate, I need to take n, I need to divide by n tilde. So if I can achieve the mutual information between x and if I can achieve this, b to the power of k, then this is just equal to the mutual information divided by k. So this is really a normalization by the code length, because the rate is defined as the number of information bits divided by n. So the rate is an average. This is why we normalize. But at the same time, the capacity also involves maximum. It is the maximum achievable rate. Okay, so this is the reason. Okay. So as I mentioned, this is not considered to be a full solution because we cannot compute this. We can compute the lower bound, the single letter Cholevo information. Furthermore, let's look at a special class of channels. We say that the channel is entanglement breaking if the output state, if the channel breaks the entanglement between the input and the environment. This is called an entanglement breaking channel. And then Peter Shaw has shown that if the channel is entanglement breaking, then the capacity is just equal to the Cholevo information, and we can compute this. One simple example of an entanglement breaking channel is a measurement channel, right? The output is classical. It cannot be entangled with anything. So for measurement channels, we can compute the classical capacity. But it's actually a pretty wide class of channels. It includes many channels. Okay, let's look at an example, another example. So this is called the qubit erasure channel. With probability of 1 minus q, I get the qubit state as it was. And with probability q, the qubit state is replaced by a new state that is called the erasure state, E. And this erasure state is orthogonal to the qubit state. It can be a simple model for photons that are lost, for example. So before I give the result, I'd like to give some intuition. Since the erasure state is orthogonal to the qubit state, Bob can perform a measurement that will determine whether there was an erasure or not with certainty. Okay, he can know with certainty whether there was an erasure or not. So let's suppose for a moment that there is feedback. What does this mean? It means that Bob can communicate with Alice as well. In the other direction, they have this back channel. So now, whenever Bob measures that he has an erasure, he will tell Alice, please send me the bit again. Please repeat the transmission of this bit. Okay, so now, by the law of large numbers, the number of erasures is approximately n times q. Q is the probability to get an erasure. And therefore, Alice will be left with n times 1 minus q information bits. The rest of the block will be all repetitions of the same information bits. Okay, so what would be the rate? The rate would be 1 minus q, right? Again, I normalize, divide by the co-length. So we see that if we have this feedback, if we have a back channel, we can achieve a rate of 1 minus q, and it's pretty straightforward, right? It turns out that we can achieve this even without feedback. This is less trivial. Let's see how we get it from the HSW theorem. So if we choose this ensemble, we choose the states 0 and 1 with a symmetric probability distribution, you can look at the output state, and then you will see that the entropy is equal to H2 of Q plus 1 minus Q, and the conditional entropy is H2 of Q. So if I subtract them, I get the mutual information, 1 minus Q. Okay, therefore, the capacity, we said that it's bounded from below by the whole level information, and this is bounded from below by 1 minus Q. Because if I choose a specific ensemble, it will be lower than the maximum overall the ensemble, maximum value when I maximize overall the ensembles. Okay? And you can also show the upper bound, but I skipped this because the proof is longer. So if I combine this lower bound and the upper bound, I deduce that the capacity is equal to exactly 1 minus Q. The lower bound is called achievability part because I showed that it is possible to communicate at this rate. And the upper bound is called the converse result, a negative result. We cannot do better than this. Okay, but together we get that this is the optimum. Okay, so we can compute the whole level information for many examples. The depolarizing channel, erasure channels, dephasing channels, amplitude damping channels. In the continuous variable case, we can compute it for a bosonic channels. There are many channels where we can compute this. Furthermore, in all of those cases, you can show that this multi-letter formula is the same as reduces to the single letter formula, right? And you asked me before whether we can prove it with a product state, right? We can do this for all of those channels, and therefore we don't need this multi-letter formula. This raises the fundamental question, does it hold in general? Okay? This was an open problem for many years. Fukuda and Wolf showed that this is equivalent, the question is equivalent to additivity. That is, if the whole level information of a product of two channels is equal to the sum. Again, people believe that this is true for many years. And this is related to the question, should we use entanglement in the transmission? Do we need to use entanglement, or we can just use a product state? One of the most popular, or maybe I should say the most popular book on quantum computing is the book by Nielsen and Chuang. This is what they say. It is believed by many researchers, but has not been proved, that allowing entangled states, signals, doesn't increase the capacity. Okay, they wrote this in 2000. Today, we know that this is not the case. We know that there exist two quantum channels with a superadditivity property, and this implies that the classical capacity does not equal to the whole level information. So I think that you could say that today what Nielsen and Chuang write is a bit misleading, because it. No, they say many researchers believe in, but we don't believe.
Why isn't the corollary that it is strictly?
Why is it? What? No.
The corollary should be that it's strictly larger, no?
Yeah.
No, because strictly
But
larger only for some cases.
yeah, for some cases. There are many cases where it is equal. No, yeah, okay, the theorem was that it is larger. In general, it's always larger than or equal. Here I say, okay, I should have written there exists a quantum channel such that the classical capacity does not equal to the whole level information. But the point is that the whole level information is not a full characterization of the capacity like people believed in for many years. This was only shown in 2009. So the full characterization is an open problem, a big open problem. Yes?
It seems like a big achievement. I don't understand why it's surprising, because maybe I missed something, but if I send you qubits and I don't tell you the basis, and in the other, in L, for example, I just tell you the basis, so you don't have information in front of them,
No. This is not what we do. We choose encoding and decoding operations, and we let both Alice and Bob know what they are. There are no secrets about the encoding and decoding mappings. So Alice knows what is the ensemble. Bob knows what is the ensemble that Alice is using. Bob doesn't know what is the information that she is encoding. Okay, I hope I understood the question properly. But I mean, I guess it's because we are sending classical information, so it may seem like we don't need, and also because the channel has a product form, that it seems like maybe we don't need to use a product state. And another point that will increase this belief is that in the classical case, Shannon also used the product distribution. He chose the codebook at random, but he used the product distribution in order to achieve the capacity. So he used a codebook where there is no correlation between the different inputs. So people say, okay, maybe in the quantum case it should work the same.
Right? Just give an example, simple example, so I understand.
When this is not equal?
I think I don't understand the statement.
The statement.
If you could give an example.
For when this holds. Okay, that's a good point. There is no example. Okay? So how do we know that it's true if there's no example? What, sorry?
Probabilistic proof?
A what?
Probabilistic proof?
Yes, exactly. They chose channels at random. They chose one channel as the unitary mixture and the other channel as the complex conjugate. And then they showed that with not even with high probability, with positive probability, you can get this, which means that there exist quantum channels that will satisfy this. So we don't know we don't know which channels can satisfy this. In Cholevo's book, he writes that it's not clear if there is practical implications to this, if there are any practical channels that satisfy this. And also the proof involves dimensions of the size 10 to the power of 32. But they try to improve it, but yeah.
So if we restrict ourselves to family of codes like linear codes, then we have also results about that. Maybe in that case the bound is.
I mean, in the classical case, we know that you can limit yourself to linear codes, and then it doesn't matter. You don't lose optimality at all. Okay. I'm not sure about quantum codes. I'm not sure. My guess is that it's true also, but I don't know.
Is it believed that such two channels are efficient to compute, or is it?
I don't know anything about those channels, other than that they are a mixture of unitaries. Okay. Nevertheless, there is a restriction that can help you calculate the capacity, and that is if you say that you have sub-blocks that are in a product with each other, which I think is reasonable for, since currently we have quantum computers of a very limited size, I think it's a reasonable assumption. And in that case, if D is small, then if the size of each sub-block is small, we can compute this formula. Okay, now let's look at those simple special cases. If we have an ideal channel, a channel that sends the qubit as it is, then the capacity is equal to 1 information bit per qubit transmission. If you transmit a qubit, there's no noise. You cannot send more than 1 classical bit. This means that if you have perfect quantum memory, it can only store 1 information bit per per memory qubit. Okay. Otherwise, you would not be able to recover the original information. Okay, now, I mentioned on the first part of this tutorial that there is another interesting question of sending quantum information. Okay, here Alice has a system M that has the state rho M, and we think of this state as a quantum message or quantum information that we want Bob to recover. Again, there are encoding mappings, and then Bob decodes. So he prepares this state, sigma M hat, that should be as close as possible to the original state. So now when we look at the performance, we have a quantum rate. This is the fraction of information qubits per transmission. And we have a quantum error, the trace distance between the state, the message state, and the state that Bob produces, that the decoder produces. Okay? This is closely related to quantum error correction for fault tolerance that you've seen in this conference. Yes. You look troubled.
Yes, I don't know what is, but now everything that is being transmitted is quantum, right?
Yes, the message is
What
quantum.
is the information qubit?
The original system M has K prime information qubits. Though I call them information qubits.
That's it. So, okay.
And if you add entanglement, then this would be a generalization of teleportation, where Alice has a qubit state that she wants Bob to recover, right? This
So,
is,
so K prime and N are given a priori, or they are the result of the protocol?
well, for every code you have a different K prime and N, and we would like to characterize the best rate of information qubits per transmission, the K prime over N. Right? Just like we've seen in other tutorials on error correction, right? You want the best rate that you can get. For fault tolerance, it's fraction of logical qubits per physical qubits here, right? Here, it's information qubits per quantum transmission, not necessarily qubits, but a similar idea. Can we look at the error? Although you can look also at the fidelity, it doesn't really matter here, because now we define a quantum achievable rate as a rate that allows the error to go to 0. So we want reliable quantum communication. And now the capacity is the maximal achievable quantum rate. This is called the quantum capacity, CQ. That's how I denote it. Okay, and now can we compute the quantum capacity? Let's see. Here we define this formula. So we look at the coherent information and we maximize over entangled states, phi, A1, and A. A is the channel input as before, and A1 is an ancilla that has the same dimension. Okay? And then we have the output channel, the output state, row A1 and B, after we apply the channel. So we need to compute the coherent information from A1 to B for this joint state. I'd like to remind you of the definition of the coherent information. The coherent information from A to B is defined is equal to minus the conditional entropy of A given B. Remember that I told you that there is practical implications to the negativity of the conditional entropy? This is it. Only if it's negative, then we can achieve a positive rate, if the conditional entropy is negative. Only then we can send qubits. We can send qubits only if we have negative conditional entropy. And negative conditional entropy can only happen if we have entanglement. So the state phi must be entangled.
Well, what if Alice just ask DHL to take the qubit to Bob without entanglement, without anything? What's wrong with it?
Sorry, what?
She transmits them physically, you know.
Over a noiseless channel.
I don't know. She takes a box, put them, and then...
That's a noiseless channel. You have no noise. You don't have, for example, if you have a depolarizing channel, right? Not completely depolarizing, with probability of 1/3, or even this channel. Okay, let's suppose that you have this channel. You transmit a qubit state, and you want to recover the qubit. Not like what we have here. Here it's classical information. But now let's say that you send a general, any qubit state. Alice doesn't even know what it is, right? And you want Bob to recover without error. You need error correction to do this. This is the LSD theorem. It's named after Lloyd Shore and David Tark. I didn't make this name up. it says that the quantum rate that is equal to the coherent information of the channel, that is the maximal coherent information value. This is achievable for the transmission of quantum information. This implies that the quantum capacity, the maximal achievable rate, is bounded from below by the coherent information of the channel. We can also get regularized formula, a multi-letter formula, although I didn't include it here. The proof is based on completely different arguments, or at least the proof that I present here. Let's look at a channel that is associated with this Steen-Spring representation. I believe that you've seen it in Arthur's tutorial, where you have an isometry from Alice to Bob and his environment. And when you throw away the environment, you get the mapping, the quantum channel from Alice to Bob. Okay, I hope you remember this. So now we will focus on this mapping, this isometry. Now, let's also suppose that the message state, rho m, has this purification, psi sm. So S is the environment of Alice. And now I look at the joint state of the output that Bob receives, Bn. So I have a joint state of Alice's environment, Bob's system, and Bob's environment. I have two environments and one output system. Now I would like to look at the reduced state of the two environments, okay? So I look at this state, omega S-E-N, environment of Alice, environment of Bob, yes?
In the last slide, when you go, yeah, so you have omega of S d to the n, e to the n. Why does e to the n has n and s does not have the same to the n? Like,
okay, you can say that S depends on, because we think of S as coming from the message, but the purification of the message state. But it could depend on n. It's not really a problem. Because the message also grows with n, so the message also depends on n. But it's not like I write B with superscript n because it's like copies. I have row A1, A2, so AN, and I write this as A with a superscript n in order to refer to the sequence of systems. Here I don't have a sequence. It's true that S depends on n, and M also depends on n, but it's not a sequence, so I don't bother writing the superscript. You could say that the mappings, basically everything depends on n. Okay, so I don't want to write it. Okay, now let's assume that somehow I managed to encode such that the two environments are decoupled. Decoupled means that they are in a product state, as we have here. Let's see where this leads. Now, this state of the environment of Bob, it has some purification. We add G. And now, on the one hand, am I running out of time? Oh, this is bad. Okay, so maybe. So, okay, so it has this purification. And I also have the original output state, which is also a purification. If you remember from the first part, if we have two purifications, there is always an isometry that maps one purification to the other. And then we assume that there exists this isometry that maps the output state to basically the information state. Okay, so this isometry can be used as the decoder. So we know that there exists a decoder, even though we haven't found it. But this is enough to show achievability. You also need to show decoupling, and this is you can do this using this formula. Now, this theorem, the decoupling theorem. If I have entanglement assistance, then I can achieve higher rates, and I actually have a single letter formula, a formula that I can compute. So it actually it simplifies the problem when I have entanglement assistance. And what I did wanted to say a word is about fault tolerance that you've seen today, and before that we are using quantum error correction for fault tolerance, right? So it turns out that the quantum capacity is also relevant there. Okay, this limits the number of logical bits, qubits, that you can have. Okay, the fraction of k prime over n, the number of number of logical qubits per physical qubits is bounded by the quantum capacity. This is a pretty recent result. It's not really surprising, but yeah. But it is interesting.
Could you explain the real settings of the computation model?
I don't have any time, so I cannot. I will just, unfortunately, I will have to send you to the paper by Fauzi, Muller, Hermes, and Chayechi. Yeah. Okay, sorry.
Okay.
Thank you.
So what are the problems?
Well, we've seen a few, I think. We've seen that we don't have a complete characterization of the classical capacity. We don't have a complete characterization of the quantum capacity either, although we do have a complete characterization for the entanglement-assisted capacities. Also, with regard to, although I haven't really spoken about error correction, but what we know about efficient codes for error correction is also somewhat limited. I mean, in the classical case, we have codes that are also used in practical systems, Wi-Fi, 5G for cellular communication, and some of them have near Shannon performance. They are optimal from a Shannon theoretic perspective, or near optimal. Okay, this is what we have in classical systems, theory and practice. Now let's look at the theory for quantum systems. You've seen quantum LDPC codes, and it is actually known that you can achieve positive rate with error that tends to 0, but it doesn't approach the capacity. So we don't know of any efficient quantum error correction codes that are optimal from a Shannon theoretic perspective of getting to the highest rate possible with an error that tends to 0. Okay.
Good. So let's thank Uzi for the and we will reconvene for